to continue a little bit what I was interrupted last time and say a couple of words about something. And I was mentioning this equation, this approximation of Schrödinger equation for molecules. It's kind of like very old classical stuff, more than almost 100 years ago, right? So it's kind of, and this is what these people say. So we are saying it usually. Some of what they say is never mentioned afterwards. And so let me say a couple of words about that. So in the Schrödinger equation, we have two parts of the energy, what the physicists call kinetic and potential energy. And kinetic is just a norm of the gradient of the function. And potential is some kind of function of your variables. And then you have an operator when you apply a differential operator, when you consider corresponding differential operator with Laplace operator, and here is epsilon. This is my notation, of course, physicists would never do it. It's small constant, and it is Planck constant, because there are these two from mathematical point of view, it's kind of differential operator of second order, and then there is zero order operator multiplying by this potential, and they're very different kind of in their mathematical effects. All kind of regularity and basic features, kind of subtle features determined by this term, which is usually dominant, like this kind of dominant term. Or there are kind of many mathematical theorems which says that this term function can be estimated in terms of the gradient on one hand. On the other hand, this comes with small coefficient, and so they balance in a tricky way, right? And if you start thinking about that, this enters, when they compare these two quantities, you have this Heisenberg principle, which is this manifestation of how high harmonic and low harmonic enter here. Again, in physics, it's rather symmetric because take Fourier transform in differential operator become multiplication, vice versa. In mathematics, it's not so. And so I want to say just two words about that mathematically, that this is a, here, in this particular instance, I don't know of any non-trivial mathematical consequences of that. You can study it for their own purpose. You can study this Laplace operator with potential and what the spectrum without any application, mathematically speaking. But there are two instances when a similar situation does have unexpected application, meaning they are not encoded some properties of a background which no operator of this kind is a priori involved. And one of them is symplectic geometry, and another one in scalar curvature, Riemannian geometry. And in one instance, you have an action in symplectic geometry in potential. And so the point there is that there is a dominant operator, a dominant energy, simple quadratic functional, and this corresponds to kinetic energy. And then this weaker term is potential, which has certain shape, some topology, and you mix them together, and there is this theory of in symplectic geometry coming from Rabinovich work on the existence of periodic orbits of Hamiltonian systems, and then developed in a more kind of elegant way, a more general way by Viterbo. And for generating function, we have action. Action in this case, the corresponding to kinetic energy term is not positive definite, it's quadratic form, but not positive definite. And then there is a weak term, but which determines the shape and where the Morse theory comes. And so you kind of couple these two things. Yeah, one carries a non-trivial analysis, and another give you non-trivial topology, and they kind of come together, and there are non-trivial consequences. And I'm using kind of personal point about that there was work by Viterbo, but he some technical points he didn't explain in detail. And so we wrote a paper with Yasha Liasberg, and half of the paper was exactly making these details. And then in the final version, we forgot to include this. So there is the same kind of gap there. And then it was it was noise afterwards. But that is a kind of a very delicate balance between, mathematically, between analysis coming from something like Laplace operator and then geometry or topology coming from this term. Here, these are things more or less clear what happens in them. In rough terms, you have this is kinetic energy for electron, and here is kinetic energy for nuclei, and then there are electromagnetic interaction there. In my understanding, so the conception of a picture is now like that. you fix some position of nuclei, and then you forget about term for nuclei, you only look at this term for electrons, you solve this equation, namely you find the minimal eigenvalue, its energy. Now energy became a function, yes, usual function on the position of nuclei, and then you minimize this function, look at the local minima. And then you can make extra kind of correction terms, but this already kind of small correction terms, but that will already give you some position of, new position of nuclei, and then you have again this minimal energy, and this must be local minimum, and then give you quasi-stable molecules. So they appear molecules as local minima of this tricky function. It's not just local minimum of this, of this term, which is just function on space, but the one which corrected with the kinetic energy. And this is, on one hand, a small term, because there is this epsilon. On the other hand, it is essential. On the scale of atom, it's not at all small, because without that epsilon, energy would be, everything would collapse, right? It's kind of not 100% obvious, right? Because you see, potential here is linear, right? It's quadratic interaction, meaning potential energy is linear. It depends on the distance between the two charges, and it has plus or minus sign here is in agreement with attraction or repulsion between particles. So I have this kind of function in inverse distances, and the fact that they have to collapse but not say diverge, it requires little kind of thinking. But already in the line, if you put positive and negative charges on the line, you see attraction will be stronger than the repulsion, right? Because all positive, and this is kind of what happens. Another point which I must admit here.
The coefficient 1/2 is crucial for this.
This 1/2?
Yes.
Well, traditionally put 1/2, yeah.
No. It's crucial because of the virial theorem. You minimize, okay.
No, it's just convention how you define kinetic energy is 1/2. Yeah. You know, there is this joke that motorcyclists running at obstruction fall down, say, "Oh, thanks for this, God, thanks for this 1/2." Yes, so what about half of the energy? It's just because there is epsilon here anyway. Who cares for this 1/2? Traditionally, because with 1/2 you integrate function 1 of x, and you have x squared. I don't think there is a deep meaning to this 1/2. And everywhere, of course, but it's conventional.
There is a virial theorem at the end, yes, but there is a virial theorem where the kinetic energy is, 1/2 or twice the potential 1/2, and then this is what makes.
Yeah, no, but this when they have a precise balance between the two, and here we don't kind of have it. Of course, but it's still the matter of convention, how you define kinetic energy. Why I put there 1/2 here, right? It just depends on the units you use. Change your units, and there will be no 1/2, no? I think it's a matter of how you choose the units. 1/2 fits with these units to have the simplest formulas. But change the units of the speed of momentum, and you have, I think it's purely conventional. But anyway, I keep it, yeah, it's always written there. So it just remind you of the origin. But here it's not essential. But the point that molecules appear in this kind of funny way, and so if you haven't this term, forget about this, then you would collapse, and it certainly doesn't happen. And moreover, not only you don't collapse, but you know the size of the molecules, when you solve this equation, will be actually bigger, more or less goes proportionally. It's like tightly packed things, so it goes like square root of the number of molecules, their diameter. And but what is not incorporated in this picture, it's not said explicitly, it's spin, and spin of electron in the Pauli principle. So you know that. But I never saw it explicitly stated. Do we have here not the minimum of the spectrum, but the minimum of the spectrum of anti-symmetric functions? Right? You can permutate electrons; they're indistinguishable, but the functions, the wave function which is responsible for them, is anti-symmetric in these variables, and this is essential for the stability that it wouldn't collapse and give you some estimate. But how it's, I kind of haven't seen it written properly. Of course, you have to say this, yeah. And indeed, if you look how molecules are formed, the fact they form the way you know that the electron typically, you have shared electrons and they come in pairs because they're plus and minus spin. And well, I know these words, but don't really understand them. And how much it would change the result, yeah. For example, the diameter of molecules. If you ignore anti-symmetry, how much it still wouldn't collapse. It cannot collapse because this term wouldn't allow collapse. You can show it for any eigenvalue. But why you need anti-symmetry? How much it changes the diameter of the molecule?
It changes a lot. There is a theorem by Lieb. And
I know the theorem. I know of course, it's Dyson. It's Dyson theorem, and Lieb who gave another proof, but I don't trust it. Not that it's incorrect, but in the kind of full interpretation and how insignificant of that. Yeah. I mean, I haven't thought much about that. So when physicists do some mathematics, you should do it the most complicated possible way. And this is something that might be completely trivial. If you look closely, usually it happens to be very simple. But this requires, of course, thinking. It's simple a posteriori. I haven't studied this. It always kind of very, with some pompous, express the stability of matter, but you know it's kind of obviously because this term doesn't allow collapse anyway, right? Because you cannot have localized function with small gradient, and there are obvious inequalities. Of course, you must be careful about the nature of that, but especially in dimension 3, they are very simple terms, which you can estimate, and you know what are extremal configurations. You know what molecules are, and the stability must tell you how this is an extremal form corresponding to actual molecules. And there are many simple questions here. I don't know how much physicists thought about that. And once you understand them, all the stability might become completely obvious if you have the picture mathematically, which I don't have. But I want to say that there are two other examples in mathematics when you don't just compute the spectrum, but you derive some corollaries. One I mentioned in symplectic geometry, and this is how we add this action, sometimes find dimensional approximation of the simple action in the symplectic geometry, just pure action without potential. And then another one, it is with Dirac operator. And when you have Dirac operator and you add potential, and this potential gives you kind of tremendous information about geometry, everything. And the principal term Dirac is responsible for the kind of basic analysis, some property of the spectrum, specifically the implicit function theorem. And what is remarkable there is a shadow, kind of classical shadow of that in the language of minimal surfaces, where also there is a principal equation. It's not Dirac, it's not Laplace operator, but minimal surface equation, also second order, highly nonlinear differential equation, but there is also potential term, and this potential term reveals geometry of the object being applied. So, and I don't know how to see this all on the in general terms. After all, you see here, if you look what happens with catalysis, whatever, you cannot avoid looking at the interaction with the electromagnetic field, because there are photons when you go from state to state, and the full picture I understand must involve quantum electrodynamics, which I really don't know. But this is just, I'll think more about that, maybe can say something acceptable by mathematicians in this respect. Yeah. For example, how many different local minima you have? How much this term have effect on this local minima? It probably grows exponentially with dimension, and but how stable they are, how deep this local minima, etc. There are lots of general questions, but I don't know. Yes, distribution of points only with this potential, it's also highly non-trivial. You know, the optimal packing, putting the points in the sphere, so they have kind of minimize this kind of potential. You know what stochastic answer is. We can compute it stochastically and so know what it is generically, but I think still there is no constructive solution to this problem, right? I haven't looked at this for a long time, so I don't remember the details, but I think the last I looked at this, people had no constructive solution. So you can see the charges on the spheres. We want to minimize energy, how they distribute, and stochastically you know what it is, but without solution. Okay, so this is a subject of mathematics which has no direct, it's kind of appeasing biology when you think about enzymes, where the level of mathematics become by far more sophisticated, and has not been resolved. Still, my understanding, people don't understand truly how enzyme works, and they make this kind of works. They model this and model that. And I spoke actually to some people in chemistry. They have rather strange ideas about physics. What they say doesn't just contradicts to usually to the second law of thermodynamics. So the way it's being described, this and so. So I couldn't find this really mathematically palatable explanation, even of course heuristic, of how enzymes work. So my understanding, it depends. At the last moment, I see, of course, on the time scale, usually enzymes work between millisecond and microsecond. A millisecond is not that fast. But however, it does depend on the oscillation, probably depends, crucial oscillation kind of molecules, which may be on the femtosecond scale, much faster, and that's how they match. So it's quite interesting, exactly because there is numbers of different order of magnitude. Actually, in biology, it's everywhere on a different level. We have strong and weak interaction between molecules, covalent bonds versus weak bonds, and kind of all life and cell depends on that. But when we come to enzymes, it's again two different scales. And here also, by the way, this you can write this represent equation in this form because there are high separation of mass between electrons and nuclei, 2,000 times roughly. Okay, now I forgot some names when I was thinking. There was a name of Lawrence, which I put it in perspective. Some interesting mathematics, which has to do now, did come from kind of biology. And so the first name in there is the guy which I've forgotten. When I'm speaking, for some reason, it's not mentioned too often. It's Verhulst. I know how to pronounce his name, yeah. This was happening about 200 years ago, that he studied, so what he was, I quote him, yeah, that he looked how population grows, and he was kind of arguing with Malthus, and saying, Malthus wrote this exponential equation, but when there is saturation, of course, resources go down, and so population doesn't grow that fast. And again, he kind of also unaware that, of course, Malthus was not the first to say it. Malthus was objecting to what Condorcet was saying that and explaining what to do with that exactly about population. And in his point of Malthus was to say that it was not mathematical but purely kind of political, that you cannot make poor people richer. They remain poor because there are social conditions as they are. And by the way, as you know, the ratio between poor and rich, it doesn't change. Very little change with time. Yeah, always there is the same gradient. And but Verhulst doesn't care about this kind of social things. He's a mathematician, and he introduced these two equations. What the hell is happening here? No, this is Lawrence already. So first he started with this differential equation, and so it's exponential growth, but when you go to some beyond some point, the growth slows, and then there is stabilization, of course, yeah. So mathematically, in dimension 2, it's two-dimensional differential equation, and then you go to the limit cycle, right? And kind of fundamental theory of Poincaré-Bendixson theorem said that under kind of natural condition, if dynamic goes in a stable region, either you go to equilibrium or you run the limit cycle. So there is nothing kind of fancy happening, rather expected behavior. But then later on he looked at the simple model, and then there is no stabilization so simple, and I haven't read carefully what he said, but certainly he realized something funny happens. And this funny happens now is called chaos. I don't know exactly how much he understood of that. And usually when you write this equation, even say in Wikipedia, for example, his name is not mentioned. They mentioned many people involved in that, like Lawrence, who never wrote this equation, or May, who wrote this equation. But this guy is never mentioned, but he certainly was highly not trivial character. And so he kind of emphasizes a good example, indeed, how America grown up exponentially.
Iteration map here?
this is a kind of logistic equation, and here is a logistic map. They are called. He introduced this terminology. They are very similar in spirit, like this equation and this map. But here, however, if you don't go to infinity, either you run into equilibrium, fixed point, or to go around the cycle. Right? This is kind of famous non-trivial theorem, von Karabin-Nixon theorem, and then there is this quadratic mapping. So, which was so much advertised by Robert May and then by Mandelbrot, yeah, with all this kind of funny behavior at infinity. And then chaos kind of come from deterministic equations. And in between there was this equation on Lorentz, and how it's a model description of atmosphere. And again, Wikipedia gives out these two people who help him to make numerical analysis, on the basis of which his conclusion were made about this highly unstable behavior. But usually, though the discrete equation was never written, of course, again, non-surprisingly, three variables. In two variables, it couldn't happen because of Poincare-Benixon theorem. And then there was kind of this paper by Robert May, who, unlike, look what's the name I always forget, Quest is also about life, about biology, about ecology, and he kind of wrote an introduction to his rather longish paper about complicated behavior of this equation. But the fact that it's complicated, of course, was known 150 years, almost 200 years before him. Actually, again, he is very much respected in physicist community, and partly by biologists, because he was a physicist and he has non-trivial mathematics, and he analyzed in a highly non-trivial way ecology in a mathematical way. But my impression, talking to people who work by ecology, said that his equation and what he wrote completely beside the point. And also all this phenomenon, also subtle phenomena about tricky behavior at infinity, this non-standard attractor for this map, absolutely immaterial, because there are so many factors in biology which influence the behavior that's much greater than this mathematical subtleties. To give you a rough idea, in a second we see other equation used and having some interesting consequences. But so what I want to say at this point, so first again, coming back, by the way, to Malthus, and when it comes to human population, or even to any population, immediately people become very emotional. So about Malthus, most articles you see are written from political perspective. So people accuse one another of some wrong political stand, completely disregarding the properties of the function involved. Yeah, it's kind of, this is also kind of funny, really insulting in a very unpleasant way. And this is the argument when we speak about Malthus. We speak if population grows exponentially, or it will stop. And it stops not because of saturation, as you know, basically because of the education of women, which actually was a suggestion by Condorcet about more than 200 years ago. How to stop population growth and will be implicated. Condorcet never mentioned also. I don't know if he in France people ever read his memorandum, Condorcet. He wrote a fantastic memorandum about the development of human culture when he was sitting, I think, in prison, or before he was arrested. He was died in prison during the revolution. And he wrote a very fascinating, very temperamental, about 100 pages, history of development of human ideas, human culture, and everything, and making some projection to the future, which are relevant to the same day. And then there was read by Malthus, who was more conservative, and saying, oh, his nice perspective wouldn't work. And now modern people just have this political discussion about exponential function. If exponential function truly exponential, or it's just political bias of certain people, they say it exponentially grows. But that we know, that was mathematical already done 100 years ago. We discussed this matter. It's interesting how much degraded actually the subject matter for the last 200 years. And also the May, what he's done, he just looked at this equation again. I think he never mentioned the originator. He knows the work, the terminology of logistic equation, but he never mentioned this originator of that. So I haven't studied this work of May, but I don't know how to test it. And the interesting story about ecology is what happened in I forgot, Whitestone, whatever park it's called, Yellowstone Park, yeah? Yes. No, somehow disappears from my terminology. So it was, and it might be here, maybe not. Somehow my contents not properly. The Yellowstone. So the story was the following: there was a Yellowstone Park. I don't know if you ever heard of that. It's kind of rather famous story. Yellowstone, and they, about 30 years ago, 40 years ago, they decided that they're probably with wolves, and so they exterminated them all. And then in 20 years, more or less, everything decayed. There were no trees, no animals, no nothing. It was just garbage. They turned into garbage immediately. Everything decayed because there were no wolves. And then they found out how much the wolves were controlling ecology. And there were many kind of subtle and absolutely unpredictable points. You see, even all this water region became dirty, and everything kind of died. It was, and one of the points, I don't remember all of them, that wolves couldn't attack how it's called, the elks, these big kind of deer-type animals, but they always kind of creating tension among them, so they wouldn't stay at one place and eat. Otherwise, they stay at one place and eat unless they would eat everything there, and everything died there. And so they destroyed the forest and everything green. And then everything after that collapsed, including the soil erosion or whatever. And then they reintroduced these wolves, and some, of course, were saying it's an absurd idea, and it became okay. And it came back more or less to the norm. And there were so many factors, I don't remember all of them, and they're basically unpredictable, because they were trying to do this with some island, they're bringing some population of wolves there, and sometimes they would really multiply, would be okay, but sometimes they would die, disappear. And sometimes it was happening because there was some alpha male that would have sire all other population, and then he would die, they would populate after him, and then there was some genetic problem because they were all too close one to another. There was this kind of usual problem which may come when there is an uncontrolled thing of this kind. So it's extremely tricky in what happened in ecology. I don't think just fine mathematics there is relevant. It's nice to have it in mind, but it is not the core problem which arises there. Then I wanted to say a few words about Mendel. Would be about Darwin first. Yeah, this about Darwin. I think I said everything about that. And about Mendel, I want to mention some problems. How it's, yeah. Another, of course, I think how different these two subject matters are, but there is this Mendel map. Yeah, this again I want to emphasize, it is a kind of pretty map. And it is again, although it's ecology, but this kind of instance when it's kind of, there is a pure part of that. And so mathematics is so nice, yeah. So there is this very simple map. You have matrices and you space, quadratic map in the space of matrices. And this map is idempotent. Square of this map equal to itself, and which kind of contradicts to logic of evolution, meaning in the changes which happen in the first generation will not repeat in the second. They will stabilize. And this was, in particular, Wallace, who was one of the co-authors of evolution theory. He was very unhappy with Mendel and believed it just kind of completely destroyed the whole evolution theory. He certainly changed it significantly and made it more mathematical and more interesting. And, no, but where is, yeah. Then this concept of this map in different terms generate this idea of Mendel algebras, and in particular Jordan algebras of this kind, right? And this particular mathematical problem is still unsolved. This problem by Bernstein of existence of such maps, but I just cannot. Where is somehow jumps? I have proper difficulty going to the right place. Where is? No, for some reason I don't have enough control over the position here. Yeah, I want to find this Bernstein problem. Okay, the Bernstein problem is a question. We have a convex domain, actually simplex, maybe in domain, and we have a quadratic map, just quadratic map into itself, and such that so simplex goes into itself, and it's a quadratic map, and you want this to be important, to describe all such maps. And that's the problem, and it's still unsolved. It's done, I think, in dimension 3. Of course, interest to this problem questionable. We understand it's a kind of semi-algebraic problem. So, in principle, for any dimension of this algorithm, but you don't expect something really interesting. And people kind of worked on that. And this is the big volumes of people say it, mathematical theory of population dynamics or population genetics, and kind of prove this kind of theorem, and I don't think they have of any relevance to biology. And so it's questionable mathematics, but in a way it's kind of amusing, yeah. Like this, classifying the Bernstein algebras. Okay, so there is some quite amazing mathematics involved there. No. Okay, here is a problem. I think this you can see this written there. So, and of course, because there are this beautiful example of Mendel map, and it is in algebraic geometry, the image of these maps are kind of special essentially have some quadratic form which squares with the linear forms, and in the simplest case of that, and this is called Veronese variety. It's sphere mapped, if you look at the projectivize it or normalize it, it's sphere mapped into the Euclidean space of the n-dimensional sphere goes to the space with dimension about n squared over 2, and it's the map symmetric, so it's projective space embedded into higher dimensional space in a very symmetric and very kind of geometrically not obvious way. It's not like sphere, it's kind of twisted, but still highly symmetric. And it is one of the basic geometric shape as fundamental as usual sphere, because it plays a role in quantum probability theory. I mean, in entropy, it replaces the set of vertices of simplex. If usual probability theory, it's about simplex, so probability kind of standard simplex in the Euclidean space, positive coordinates and sum equals to 1. The extremal point of the simplex and the probabilities are a combination of these points. The extremal point there and corresponding kind of unitary or orthogonal version of that, when you consider positive definite matrices and the extremal set there, are exactly the Veronese variety. It's a convex set of positive definite matrices, and normalize them if you wish to have trace 1, and then you have extremal points is Veronese variety. So it's kind of one of the most fundamental objects in mathematics, and not sufficiently advertised in the kind of in textbooks. Yeah, my impression. So it's something that if you give a list of 10 geometrically, mathematically significant things, it will be 1. It will be Pythagorean theorem, sphere, and dimensional space will be force. Yeah, it's one of the most fundamental objects in mathematics, and it's not somewhat unexpected properties if your intuition based on the spheres. Okay, we finished with that. It's more or less continuation it was before, and now I want to turn. No. Okay, this is not the equation. Now let's continue with ecology. And this is variation of these previous equations, and which came later. And this is a quite natural equation, very similar to what happened in molecular dynamics in chemistry, when there is mass action equation. So that says that if there's some particles here and particles here, or animal here, when they interact, but for example, one eats another, or some chemical process, the number of this interaction proportional to the product of the densities of the two of them. And this is, so this predator and the prey, and this quadratic is bilinear form probability of their meeting. Actually, the bilinear stuff was also in the Mendel equation. So, and this was an interesting point of this equation, exactly in this form. So it's a very special differential equation. Amazingly, it has periodic solution. And this Volterra who proved this. Lotke, who first invented this equation, and then Volterra had been done kind of independently. And what's interesting, which is biologically kind of amusing slightly, that you may have situation where you have predator and prey, and this population may oscillate. You can swing it maybe either of the two things. Either predators consume all prey and everybody dies, or predator will not catch enough and also dies, but it's not true. It may oscillate, as seen in this differential equation. But again, it gives so poor approximation because there are so many other factors. It gives a rough idea what happens. But certainly it cannot, and the fact that there is a solution, it's kind of not completely trivial. But if you properly analyze the equation, you can exclude one variable and then find explicit solution. It's some exponential function, of course. It's corrected exponential function. If not for quadratic term, it would be exponential solution, and you can solve it explicitly. And it's kind of it's not terribly exciting, but it's there. And then there are examples, so some biological example related to that. So this equation allows you, it does not applicable in any quantitative form, but if you have very naive thinking if you introduce more predators and immediately everything will be eaten up, it's not true. It's because, or even in this simple model, it may oscillate, and in the real world it may be even less true. So it is not, God doesn't give you positive information, this mathematics, but suggests your caution when you try to predict ecology, right? And here is some example. And then there was equation was generalized, and there is Kolmogorov equation, and lots of study was done of this equation, and I cannot judge their biological significance. I suspect suspicion very low. However, it's interesting, yeah. So, and there are this kind of interesting, actually biological effect when you apply some pesticide, that the effect may be opposite. You want to kill some pest, but in a way, first you more, the consumer of this pest may suffer more, and this happens all the time. When you introduce pesticide, the effect is opposite to what you would think. Things are not monotone in this world. When there are many variables, very easily you develop periodic or quasi-periodic behavior. So, and this is what this mathematics suggests. And again, it's huge literature about that. Mathematical literature, well, huge, well, quite significant, I would say. But it's, from a mathematical point of view, it's on one hand, when you have complicated differential equation and predict its behavior, it's always difficult. But on the other hand, it's kind of rather straightforward. When people discovered this chaos, it's unclear to me why people were so much surprised, why it shouldn't be. I understand, on the contrary, when they found that solar system may be not ergodic, and there might be some big periodicity which we observe, and that's really amazing, right? And this Kolmogorov KM theorem, which is, of course, and still not proven in the realistic planetary system yet. Which there may be also other factors, of course, influencing there. But why was there any surprise about chaotic behavior? Genetic behavior is always chaotic. You see it everywhere. Because people sometimes in classical times were loved writing explicit solution, and they emphasizing equation they could solve. So if you cannot solve it, immediately modify it without trying to say they are chaotic. But of course, if they are chaotic, well, what can you do? you cannot do much with them. And this is about that. Now I want to give some quotation of some people on about biology, yeah, essentially about kind of basic biological principles. Many things people said, and so I start with Weissman, because he was one of the kind of founders of modern evolutionary theory, and actually he, in my view, shaped what we call now the Darwinism. He was criticizing Darwin at many points, and most of what Darwin said was not correct biologically. He was kind of having nice philosophical ideas, conceptual ideas, but technically what he was saying was incorrect, and Weissman was correcting it. And in particular, he suggested, he brought in idea of information in biology. So here is what he says. So he explains why acquired traits cannot be inherited. And because they said in completely different terms. On one hand, there are some phenomena in the world. You eat something, and then there is something in the cell of your body, and they follow a different language. And he was saying it's such absurd. If there was some machine, like on the telegraph, and then you write message in one language, you apply it in another language. Moreover, not only you do it in another language, but you have to implement action without understanding the language. And this was his logic, and also he was making some experiment, because common opinion was that if you cut a tail of a dog, then the children do it systematically. The following puppies will have no tails. Yeah, people believe into that. It's fantastic, by the way, what people believed, both in physics. You know, the law of inertia. As we know, people believe that if you throw a stone on a moving ship, the stone goes like that. People believe that, yeah? I mean, there is no absurd, people believed. And there is, as I said, principle by Haldane, articulated by Haldane. If everybody believes and says everybody is true, must be nonsense. Not only is probability will be half and half, but much lower. It says there is a mechanism in the mind why people believe this way, and most likely, among all other causes, it can correspond to reality. So if you know something, everybody says it without reference, must be nonsense, if there is no reliable source. That's a principle, and in particularly that, Weissman made a cruel experiment, cutting tails of rats or mice, I don't remember, and certainly nothing happened there. And so he kind of, and nobody would believe it would happen, and actually it never corresponded to what Lamarck thought. And then if sometimes you say it kind of Lamarckism versus Darwinism, which absurd. Darwin was exactly on the same side as Lamarck, and he was believing it will happen, even giving some completely inadequate explanations. On the other hand, I can here defend Darwin, he also realized that this naive, straightforward kind of scheme of natural selection does not explain evolution. Just give you some framework, explain nothing. And biologists sometimes say explain, which is an absurd statement, and explain nothing, and Darwin perfectly understood that. And he was very unhappy with that, and he tried to find some explanation, to find some logic, but he couldn't find it. Justified it was very, we still don't know why it works, it may work so fast. Right? And in the case when evolution grows fast, there are specific factors, very often the sexual selection, which accelerate evolution. And when I was mentioning that evolution, which we saw in our time, is that there are mosquitoes who live in the cities. 100 years ago, there were no mosquitoes in the cities. It's a new kind of phenomenon. And apparently they even cannot have children with wild mosquitoes. Okay, but this is a point, and this is actually the book. Amazingly enough, it's a very interesting book. I found it, and then sometime Brauth, he wrote about evolution, and it's beautiful language, how it's written, and full of ideas. This Weissman, kind of, again, if you compare to what usually people write nowadays, by far kind of more interesting to read, because he knew much more, and saying, and discussing it. Then there is again pretty good. This is also quite bright biologist who used to be electric engineer, and so I suggest his reading. So, and then of course, the famous book there is, so he explained different aspects of information in biology. And then there is, of course, the famous book by Schrödinger, What is Life, and which has apparently large influence on biologists, but it's unclear again. Usually kind of fame attached to some point. Essentially what he does, he repeats what was done by his colleagues also, physicists and biologists, and explains something about physics, what you can expect of physics or what you cannot. Right? And for example, he explains why atom must be small compared to you, and so what happened if they were bigger. But one point he does exactly, one very essential point he says, he does that gene must be connected by covalent bonds, but not by weak bonds. So they cannot be like protein. Information cannot be encoded in the shape of the protein, because I don't know exactly, by that time, I think already was the Pauling theory about between different nature of chemical bonds. I think by the time he wrote the book, because protein kept by weak bonds. They're slightly stronger than van der Waals bond, but still are weaker. They called hydrogen bonds. They're kind of semi-covalent. They're not exactly interaction between dipoles, but only slightly stronger. But still, they comparable to KT energy of moving molecules, so it can be easily destroyed, and so information will be destroyed. But you need covalent bonds whose energetically by order of magnitude stronger. And order of magnitude stronger means that their time life infinitely stronger, right? If you increase energy by 10, the time life goes by a million of years, right? Because they go into the exponent. Or the probability of decay, energy goes into exponent. So it's a huge difference. And then so he said it must be aperiodic crystal. So something, and again, it's correct. The prediction, it should be kind of one unit or few units. There are not many proteins, identical proteins, but essentially there is only one DNA in your body. Well, it's 4. Of course, it's 4. But even in chicken, they have about 70, but still a small number compared to number of typical molecules. And that was one essential, I think, point by Schrödinger. He also said, well, it's non-equilibrium. Thermodynamic is non-equilibrium. And then being repeated many times, of course, non-equilibrium. Who is equilibrium mean? To say something in non-equilibrium, to say something in equilibrium, it's a statement. To say negative, well, it's a generic case. And he just mentioned that, but this is being repeated incredibly many times. Certainly it's not an essential feature of life. Right? Anything which is not that, everything which moves in non-equilibrium. And this was said in various terms much more. Another point he makes, this stability of naturally selected genes, this is what he says. It must go from generation to generation, loss of replication, and it must be still stable. And only covalent bond can achieve this, and still extremely, we don't understand how the hell could come to life. There are many models, by the way, for appearance of life, because if you want, again, this is the process of replication of DNA involves many proteins which have enzymatic properties. And it's not just enzyme chemical, they're also kind of motor proteins. And to have such an enzyme, probability of this, so once you have it, so conjecture is one of the conjectures, one of the versions of conjecture of so-called RNA world, that the world came first in the form RNA, and RNA could serve both as keepers of information as well as enzyme to have replication. And of course, it all only makes sense if there is a flow of free energy in a very suitable chemical form. Nobody discusses that. They take it for granted that there are nucleotides with a phosphorus part which keeps energy, which is not so easy to have in natural condition. You need some chemical source of energy, which is possible but not so trivial. But to have such enzyme, probability is basically 0, right? It couldn't happen because this enzyme must have about 200 or 300 nucleotides. It's too big to appear on random. But then there are various models how we can bypass it. It's very interesting mathematical problem that you want to build, to find some pathway, to build long chain out of small one using some basic operations. And what simple condition, whatever they mean, global condition, we have to add to make this possible. And about 10 years ago, it was discovered that you can produce the nucleotides may appear in natural way. So you just modify global parameter. You don't have information. We don't know what to do. But you change temperature, or you have ultraviolet, as it was on Earth 4 billion years ago, and then something happened you wouldn't expect. And so these nucleotides can be created. Before they believed it cannot happen because the sugar backbone and this molecule exists in nature. And there are other bases also they were in nature coming chemically, but they never wanted to come together. And chemists couldn't do that. When they tried to bring them together, nothing was happening. And then, well, not by accident, they found out if you do kind of thing less carefully, so to speak, you mix things, then this happened. And if there is ultraviolet, it cleans up kind of if you do it kind of in a messy way, of course many things may happen when there is too much of irrelevant and confusing intermediate kind of chemical. But in the presence of ultraviolet, rather rigid ultraviolet, you clean up it, and then they found that RNA, basic elements of RNA could be created. The nucleotides for RNA could be created in a natural way. Natural meaning you only control global parameters. You don't have information written anywhere. And there are quite a few of these parameters, but still it's a negligible number compared to what carried by nucleotides. So this is, and so there are many models of RNA. So it's a typical problem. You can think about that. There are molecules, they can come together, may separate, and the probability they're gluing together, and probability of decay, and the certain parameters, some particular one, some particular sequence may gain and become special. Another remarkable thing was discovered. It's a symmetry. You know that how called it, the right, left and right configuration. Of course, carbon atom fully symmetric. But if you attach something here, and then you may have this mirror image, and it will be something else. And all molecules, all organic molecules in life, they have the same what is polarity. Not polarity is the right word. And it was for a long time it was not clear so why it could be so. And then it happened that if you have, for example, pairing of two RNA, they have different kind of this polarity, it will be highly unstable under ultraviolet. And that said that you will naturally have to go to this or to this kind of center of attraction. So it's a mixer for complicated molecules. If there is a mixture of two different kind of symmetries, it becomes unstable. Another kind of discovery of the time. So now chances to find realistic model of abiogenesis, creation of life, coming closer and closer. But still, of course, you need experiments, of course, to make it. But you think now, based on the basis of experiment, but mathematically, you can look at this. Yeah, and here what he says, yeah, it is also non-trivial thing. He says, it's order coming from order. Yeah, this is exactly this order in the covalently fixed order, but what you see of that, what emerges, essential thing, a protein in particular shape, and these are weak interactions, and so this order encoded by covalent bonds turns into order encoded by hydrogen weak bonds. And again, so this is not accidental, it goes this way, right? So it's like, it's kind of correspond as you have energy coming from the sun, from high energy photon, and you lose it in a low energy photons, yeah? So we don't keep, the Earth doesn't get any heat from, any energy from the sun. Everything goes back, but you change the entropy, the free energy, balance of free energy goes in the right direction. And something like that happens with information. It decays on each stage. And this is why kind of apparently life can work. So when you go, information from your DNA going to your body, probably you lose 99% of information, which is very interesting to evaluate this number. Right? On the other hand, if you formally look at your body, there are so many points you have to balance. And this happens not because of information, but because the nature forces you. The laws of physics, of material physics, shape makes particular shape. For example, how you make joints of your bones. Right? Apparently, there are so many points which must be in the right position. Already, one of those bones, you look at the microscopic level, it will take you half of your DNA. But however, it works. So that's mathematically, it's very hard to formulate correctly. And if you formulate, there is a chance maybe to check something by using the data. So order based on order, this. But this again, order of different energy level. So now there are and then there are lots of kind of discussion between those who are trying to define life. And this is of course very funny because they want to find, with emphasis, say necessary and sufficient conditions for life, which is certainly very funny. For mathematicians, yeah, the emphasis, they want to be logically correct and to define life. And if experience in mathematics said that in order to define fundamental concepts in mathematics like probability, algebraic variety, it's not just you look put there and just try to make this division like, the man is a bird without feathers. It's not kind of a definition you want. And this is usually the kind of definition they suggest. For the most part of biologists. Of course, they don't say it, they know that, but they think they're more intelligent, but they're not. And of course, it's not our point. There are so many features, and you don't know which of them are relevant, which are not, how they balance, and this is what you want to understand. Finding definitions is an absurd idea, and there is, again, some people who says this rather explicitly. So, yes, I don't want to. The Kunin is, for example, he's kind of mathematically minded, and he explain why it's stupid to try to do that. But he indicates some problem. So there are different schools of people. Some emphasize physical, chemical aspect of life, and they say life is nothing but chemical process with such and such properties. And others say, well, no, it is just some information process that with something. And in fact, of course, it's a mixture. And how to describe this mixture is tricky. Because you see, so what happened there, as I said before, there is DNA, and this DNA encodes information in how you are made, how, say, proteins, the shape of proteins. And look at this particular instance, the simplest thing. And this protein shape first you have still, you go from DNA to proteins, you lose, well, some bit of information, but not too much, I think. It's a lot because you have three bases for protein, and there's not some ambiguity for the three, so you lose kind of two-thirds of your information. But protein takes particular shape, and this shape somehow determined by this information. And so it looks kind of the number of possible shape of protein by far more than the number of bits on there. But apparently it's not so, kind of, because most of this configuration cannot be realized because of the physics of that. Yeah, we don't know exactly what the physics is, because even interaction between residues they are known, and they are known with very poor precision. And this an interaction of two local pieces of protein depends usually on several residues nearby, or even triple interaction are possible. So physics of this infinitely complicated. Even if you had this physics, mathematics will be also impossible. But for all we know, there are not so many shapes which are being involved. And well, but how to describe it and what level it happens? It happens in the space of all possible kind of conglomeration of polynucleotide chains, or only those which are used in biology, where you know already the secondary structure, third structure, the number of global structure of protein basic types, just known in the databases is several thousand. And of course, there are very few basic secondary structures, how local part can interact. There are lots of these constraints, and of course, we don't know how to say it mathematically, and how much information being transformed, how much is being lost. And of course, when protein goes to the whole body, then there is embryological development, and probably even more information being lost. And this would be interesting to say how much you need to know to describe human being. And I think we very little, just maybe 2 pages, right? If you know the laws, how to make it, right? So apparently we are much simpler, and the complexity is illusion. Like for iterating, when you iterate this logistic map, and we have all these fancy Mandelbrot shapes, yeah. But this very simple equation determines this. So we are a limit of certain iteration of certain process, and then complexity comes from mixture of the transformation laws and some mathematics. And this will be interesting. Formulate. Of course, you cannot do anything practically useful. So what is the? Yeah, it is where is discussion of what people think about life. Yeah, of course, the most complicated part is in evolution is even for proteins. At least we principle understand how proteins fall. We cannot, and now there are kind of programs based on neural networks which make us can compute that without understanding the nature. But then we come to embryological development. There is no idea actually how it works on physical level. What a physical interaction which brings the shape and turn information in genes to the shape of animals. With plants, it's much simpler. There are simple algorithms explaining much of the structure of plants, tree-like structures, characteristic for plants. For animals, is much less clear. So, okay, and this is I want to make some interaction now. We go to the next topic. Yeah, it's a good moment to make a little interruption. The first lecture speaking a little bit about biology, and now I'm coming to more abstract discussion and continue something rather abstract. And then in the last lecture, on the contrary, I come back to something very specific, which will be very far from kind of what we can call serious mathematics, namely to kind of data about the biology, ecology on Earth, just lots and lots of numbers, which interesting to know. How many people, how many mass, what is biomass, how it's distributed, and not everything is known, but very much of these things is available, and that's amusing. Yeah, you know that there are more weight-wise ants, by a factor of 10 probably, than people on Earth, but much fewer whales. Yeah, whales are just peanuts compared to ants. If you look at the mass, and many other things like that, which has changed, right? 100 years ago there were more whales than people, and now there's more people than whales, weight-wise, of course. Not and again, the remarkable thing that which I was speaking last year, and I will say about this again, but this by few lectures which I find rather remarkable, and this difference due to difference between energy between ammonia and energy of covalent bonds in ammonia and in molecule of nitrogen of 2 atoms, of course. And so there is little difference, about 5% in favor of ammonium with some other, and for that reason you can bind ammonium, and so life, as we know, it is possible, and it was kind of artificially used about 100 years ago. Yeah, almost exactly 100 years ago, and when these human populations began growing. And it's not always emphasized that growth of the population is due to one particular chemical process invented 100 years ago, and it's known the moment when it was decided, up to an hour. Conversation between Haber and Bosch. Haber discovered this kind of artificial synthesis of ammonia, and Bosch realized you can do it industrially on a large scale. And it was in 2 years he implemented that, and so now everybody who is alive depends on that. So if it stops, 2/3 of the population will die. So this process determined the change. Maybe not 2/3, maybe half. And this is just one particular kind of balance, the difference between two energies of certain chemical bonds. And I think it's very interesting how things are related. But now, so what we come to, so what kind of mathematics are there? So I want to try to list different kind of mathematics which appear, which are related to biology. And some of them, as I said, and which I mean, no, actually I haven't finished one. Wait. There is some aspect of mathematics which is, this is again the basic aspect of mathematics we have almost everywhere, including biology. Is the same mathematics you have in physics everywhere. In mathematics depends on numbers, explicitly specific properties of numbers. Even in ecology, you just look, see how often things interact. This quadratic law, make some coefficient and write some formulas. And right or wrong, whether they're applicable or not, the mathematics is very familiar. And the same stuff we should do in mathematical physics. And Holden, who was one of the first people who combined Mendelian genetic and Darwinian theory, he studied three people that were Holden, White, and a mathematician who was Fisher, who kind of developed this population genetics. And so the evolution applied to genetic pools, and now we can count the number of different alleles. So there are numbers, you may count them, write formulas about them, and actually make some conclusions. And one of the conclusions made by Holden was about some moth living in England. We changed its color in advent of Industrial Revolution because being dark was apparently better to be than being light. And then he claimed that computation showed that it was actually selection, it was not completely accidental, not just fluctuations. And of course, in certain model it's true, and probably it is true. This situation, I wouldn't say it's a deep kind of application to biology, and people argued much about that, and computation confirmed that. But this is, though it's kind of apparently subtle biological process, but what goes out of that is just numbers. You see how many children, a particular group of species produces. And just looking on these numbers, you only count these numbers, how they depend on the conditions, and see how fast they may grow in this or that model. And so this is a kind of very simple mathematics, simple in a way, traditional mathematics. In practice, when you run into, you have some just differential equation, usually the one kind of describes some quadratic equation, for example. And understanding how they behave in the long term is tricky. Another kind of point of this kind of mathematics is observation that with very high degree of approximation, the probability of acquiring by population, keeping some positive mutation, doesn't depend on the size of the population. Well, it already depends on this very little. And heuristically, mathematically, it is clear because apparently when there are, if you double your population, you have double probability, for small probability they roughly had, having this two mutation rather than one advantage mutation. But fixation of that depends on how many individuals have not changed, and their number also is bigger. And when this number is bigger, it will dominate in the long run the one who had mutation. Though it had little advantage in quality, others will have advantage in quantity, right? If you have one slightly advantaged individual and many slightly poorer, but there are many of them. If you look how this tree of generation goes, probability of extinction, this will be slightly lower, but this number is bigger. Therefore, it's still this descendants of the advantaged one may die with a higher probability. If you make this counting, you see you have more or less the same number. Depending how you make modeling, in the ideal situation, they're exactly equal. And then this makes us very unclear how actually the changes, significant changes happen, right? But it said this kind of simple model, not completely right, but there are people who believe strongly in the basis of this kind of neutral evolution, that actually the evolution more or less kind of random, what they call drift, which is opposite to terminology of what is used in mathematics for drifts of random walk. In mathematics, usually the drift of random walk exactly effect of gradient, usually linear rather than quadratic. And here drift exactly kind of Brownian motion, what's called biology. The terminology is opposite, so it must be aware of that. But this kind of mathematics. But there is another kind of mathematics which I want to say to us earlier, which I missed. Yeah, this is. I didn't say much about that, but it's sequence analysis. and genomic brought up various mathematical direction about sequences, and one of them is multiple sequence alignment. And I think it's quite remarkable in mathematics, which not mathematicians don't quite know that. For myself, I don't understand it all. So you want to compare different sequences, how close they are. And of course, if they're completely random, and if you have two random sequences, you compare them, and the probability of if you have 0 and 1s, at every point, probability of having the same will be 1/2, and they're unrelated, they're kind of perpendicular. And how to catch some relations. And then to bring groups of sequences to some groups. And it's the most kind of naive idea how you compare it pairwise and see which are close, and then you have kind of a graph, and then you cluster it in some way. But there may say a connected component, or there are various ways how to cluster a graph. Given a graph, and you can see the blocks which are internally related stronger, then they're related to between different blocks. However, this doesn't work. So very often, because correlation is so weak that for two of them you don't quite see it. But what happens when you have many of them and you compare them, and then you can see, they also have some particular common feature. Probability of this feature having for two of them will be just 1/2, completely random. But with the same pattern, you see in different sequences, even if it's very weak for pairs, but the same as pairs for many, it becomes significant. So what you replace, if you can think when you compare them pairwise, it's kind of a distance. You have a graph, or you have a metric space, and then you clusterize this metric space by kind of components, or approximate components, where the most simple and common division using the spectrum self-Laplace operator, and that kind of nodal point divided in nice pieces. And this works pretty well. But this is not a metric. It's some kind of non-binary relation between sequences. And there are algorithms adapted to biology, but there is no, my understanding, it's on one hand highly developed, on the other hand abstract mathematics here is absent. We don't know how to properly, what is the true mathematics behind it, and what are interesting mathematical phenomena where these are being used and being seen. So but this is a major tool for studying, to look at the past. Because when you compare very many organisms and see what they have in common, you can say what were their predecessors. And of course, you use the fact, when you make this comparison in biology, up to a large extent, you have idea of evolution, that they bring them together because they had a common ancestor. And the common ancestor will be just only one for many. So this bringing them into blocks have intrinsic meaning, which you have to recover. And so how it works? Right, so there are these conjectural first organism, it was the first cell from which we all came from, right? There was at some moment, there was a single cell, just single, exactly one, and we all descended of this cell. And that's kind of remarkable kind of point, yeah? And this was in some way, usually this idea ascribed to Darwin, however it was said in slightly less precise form by Buffon, who immediately said he didn't believe it because he knew it would be dangerous to believe into that. And then we kind of mathematically, it's very kind of unquestionable. Yeah, well, if you believe in mathematics, make some little counting, you see probability of having two is very low. Right? Only one survivor. And but if you go beyond that, and there was some work done recently, also using sequences about proteins which could have appeared before cells came to life. Yeah, just 2 or 3 years ago, there was this new mathematical analysis of some protein sequences and seeing which proteins were preceding this kind of LUCA. And there are, of course, 2 of them. One corresponds to mitochondria and another to something else. Yeah. And this is a kind of mathematics involved which is not it's a different kind of mathematics. It's kind of combinatorial mathematics. And this appears in many levels of studying sequences. And in particular, quite amusing mathematics is is based on complementarity between nucleotide polymer, because there is the sequences of nucleotide, RNA or DNA, and they're complementary sequences. You can say there are two letters A, B, minus A and minus B. And when they stick, A tends to stick to minus A and B to minus B, at least for sequences. By the way, it depends on the size of the molecule, because A is slightly smaller and B is slightly bigger. I'm sorry, A and A minus 1 have complementary side. One kind of concave and one's convex. They fit this way. You see it molecularly how it happens, but it happens only for sequences, not for individual molecules. And then you may think, so given the sequence, and then when there's some energy, how it's sticked to another, depending on that, and you can look what are the optimal shapes. And for RNA, there are many interesting shapes. The typical shape, how different piece RNA stick to another, and this is defining that is non-trivial. And there are some algorithms saying, so given a molecule and have this, the law of complementarity, it's a simple interaction, much simpler than what happens for proteins folding. How the secondary is called secondary structure. It's only pairwise interaction, and then the shape becomes. Next level of structure is much more difficult to determine, but this is kind of simple mathematics, and up to a point you can do it. And if you look mathematically what it is, this kind of change, this molecules create RNA are essentially the same as what people do in Riemann surfaces, how you describe Riemann surfaces by graph and band around these graphs, yeah, the same kind of objects. And algorithmically, it's still unsolved. We don't know exactly how to compute in full generality, depending how complicated they are. If you even kind of purely combinatorially, if there is kind of simple overlaps of different steps, they call pseudo-nodes, then usually algorithm works very badly. And this is kind of relevant to know the shape of this molecule, and it's practically kind of quasi useful. But this interesting combinatorial mathematics involved, which is not traditional mathematics. That's this one point about what other mathematics we have. So return to the section 2. Yeah, another interesting piece of mathematics, which is I mentioned here, is dynamics of excitable medium, like your heart. So your heart conducts electricity, but not as it done in physics, but conducts it, become excited. At some moment, then produces electricity itself, and then temporarily it relaxes and does nothing. So it's like fire in the forest, when then some trees burn and forest goes away, but then they grow up, and so forest may continue. And so this would happen in your heart, and mathematics again here highly non-trivial. And of course, it's never that simple as I described. A real model involves lots of parameters, but this intensively studied and well studied subject matter. Of course, another kind of mathematics is by physics, or physics what's happening in the cell. Something I mentioned, of course, enzyme is extreme case when physics goes really very far from biology, but there still physics is not the full story, because the biology enters in the moment when there is selection of enzyme for some purpose. And this selection is kind of informative process, because eventually it will be some encoding in DNA. DNA tells you how to fold for the protein and perform rather complicated chemical process, which we don't know, mathematically we can't compute it. Yeah, not only we cannot select for that, when it's given this protein, we cannot evaluate the quality of the synthesis, how well it works. So, and this is something. So when I finish with that, I say what is actually the ultimate mathematics we want to know. So what else? Yeah, here is a kind of, I just enlisted typical, kind of, no, not typical, but kind of common activities of mathematician associated with biology. What kind of problem being solved? I just want to, and there are lots of mathematics. So recently there was very interesting work done on olfaction, because olfaction, unlike vision, is statistical. And so a remarkable feature of olfaction, maybe I was already said about that the number of genes responsible for your olfaction is order of thousands, maybe several thousand. And the number of genes responsible for your vision is maybe less than 10. Because the huge variety of proteins involved in the receptors in your nose, because each receptor corresponds to some particular class of molecule to which stuck and produce the smell. And you cannot make few of them, right? Because smell are not ordered. This again interesting mathematical point. But probably already Misha mentioned that our vision, based on the fact that there is a space and there are marks on the space, but space itself is kind of rigid, give you rigid structure. And so this is a positional presentation information like in the language. It's not one-dimensional, maybe two-dimensional, three-dimensional, but still positional. And so you only need bits 0 and 1 and the way where they are positioned. And so you only need in your eye to distinguish few patterns, and then the mechanism ordering them, and that's it. But you don't have to know a particular gene to recognize a particular shape, right? You complicate the shape, not you have to gene for that. It's just built out of smaller units. But with smells it's different, because smells are not this information conducted by smell, and this smell, of course, the most ancient of our perceptual features. Already bacteria have kind of a smell, right? They distinguish different chemicals. And this is not ordered. And this is much more primitive, and therefore you need much more data, much more kind of machinery to distinguish smells. And therefore you need more proteins in your nose to distinguish different smells. And this again interesting point, how much information goes this way or another, and one might be curious, what is how world looks or are the smells in the nose of a dog. The dog basically perceive the world via the smell. For them, smell probably number one, not only for dogs, but for some other animals. And how they perceive the world around them. Because must be, again, understand what is the world around them. So what we receive, right? We receive, our brain receives just sequences of signals. Yes, no, yes, no, yes, no. Out of that, we make all that. And the major cause of information are our eyes. They take half, more than half of our cortex. How we build this world out of that. But imagine information comes from a different source, from a nose, when there is no order. And so what will be the picture of the world we will create, right? And the same problem, of course, related to how from DNA you create the structure, sequences being transformed to the structure. And also there is some, in this respect, conjectures how the world perceived by dolphins or other animals who have echolocation, because they see the world, they hear the world and reflection of the sounds they produce. And this is a completely different perception, conception of the world. So we believe that there's only one world around us, but this is, of course, fully 99% reconstruction of our vision. Not on that, then there are other senses. So amazingly that blind people, and there are also deaf-blind, can reconstruct, however, the world, because there are something else. Of course, there is a body perception. There is another feeling. So there is forces within the body we feel differently. And this is completely kind of different kind of perception. I don't know how much it's understood on genetic level, right? Actually, I haven't looked at that. But that is, again, completely different source of information, and which complementary to vision. Probably it's more fundamental than vision also. But anyway, with olfaction, there are really lots of mathematics inside. Kind of, which I know rather superficially. Some of them related, which I heard of, but I know. You know, there are this statistic of rare matrices with very few entries. There are n by n matrix, but only n to n entries, and what you do with them. But there is a work of Axel and in his lab and other people, which I know a little bit of. And now if we want, so what we ideally want, if we want to incorporate this kind of physical mathematics and informational mathematics. And for that, we have to imagine how, granted abstractly, without knowledge a priori what the world is, only knowing general principles, how to, looking at the sequence, to guess what it tells you to the cell, what the cell to do. So, and so conjecturally, this information all there, modularly you understand the laws of physics. But understand them, plus you have unlimited computational power, so you can implement them. Somehow, cell can implement them. And, but in principle, we don't know how to do it, because it's exactly the same problem. How you mostly construct the world around you. You have the structure in the world, lots of information received by your vision. But ability to perceive it is encoded in some process in your brain. And the input is just sequence of symbols, which goes into there. And so how the sequential information transforms, for example, to spatial information. And it is, you don't know that. Or, which is more kind of elementary kind of thing, and what happens with the, how is done with the language, how we can much recapture semantic of the language from the syntaxes. And now there are all these AI systems which kind of bypass it and behave as if intelligently, right? But of course the limitation that they have only one input, only linguistic one, while we have several input, one of them kind of physical perception or smell, whatever. And we synthesize in our brain all these three sources of information, which is much more subtle than only use sequential information. But for many purposes, you don't need it. All kind of qualified professions depends only on one kind of information, which is danger for qualified people from it's artificial intelligence. Now, so like now about numbers. So just understand what kind of different mathematics can be. We have to more closely look how mathematics enters, for example, physics, and numbers, of course, are essential. And number and spaces, and we mentioned that numbers are, from a certain point of view, are impossible. So if you enlist properties of real numbers or complex numbers or of any kind of field, and just without knowing, can say, so you have a certain structures, with these laws, probability of this is virtually zero. So that shouldn't be there. So this is what's common between mathematics and biology. They work with objects which shouldn't be there. They are very improbable. Unlike physics, which always emphasize most generic and most probable phenomena. Sometimes unconsciously, physicists think about generic phenomena, an exception, well, just suppressed, you don't think about them because their probability is very low. Like second law of thermodynamics is the major manifestation of that. It's only highly likely events which take place. In mathematics, it's opposite, and there are many features of numbers, and their features, of course, go along with mathematics and physics. And then this, and here again, I'm not sure what to say. Yeah, then there is a question of language. As I said before, we want to make some mathematical language incorporating biological concepts, and so here I'm giving a list of these concepts, and then indicate their essential features. So, where we are. So here is these words. I don't want to repeat them. And then there is a question of complexity. Right. One of the issues along information, there is concept of complexity. And this, again, we don't have. We say that biological systems are regular and complex, and as was mentioned before, regular is a completely meaningless concept. Apparently, just used metaphorically, and we don't have any material, meaningful incorporation of that. But about complexity, apparently there is a concept of complexity applicable to living organism, but it is different. It's kind of opposite in a way to what is called Kolmogorov complexity. because completely random sequence has minimal complexity and as much as purely periodic system. And this you can, I think, justifiably say that there is a lot of noise in biological system, lots of random things which we forget, they're just noise, they carry no information. We can say, oh, it's a lot of information, this. Majority of data there is this random noise. It's either random or it's random modular physical constraints, right? And then there is something which was actually encoded in DNA and sometimes epigenetically. It's a big issue, of course, how much truly inherited in DNA and how much is kind of slight modification of that. And again, it's sometimes people over emotional in biology about what is true, and again, depends on their political views, what they believe is actually true, and it's hard to measure. But definitely there is an issue of complexity. Another fact, mathematical feature of biological system, very different from physical, that average doesn't have to represent typical properties of objects. So in physics, it's an unspoken rule that whenever we can compute some averages and then believe what we see is implementation of these averages. Is it true? What do you say? Yeah. Yeah. In many situations, of course, it doesn't apply to cosmology because there are individual objects and you look at them, but still, that's the principle. In biology, it's not so. We all the time, we have exceptional cases become dominant. There is little, like we spoke, an example of an egg. You look at all the structure of the egg, and we have very good idea what's on the average. However, it's not the essence of that. There is one particular cell and one particular spot on the cell in tiny little molecules, and this determines what will happen in future, and it becomes globalized. Of course, physically, this never happens. Right? There is one which you cannot no way to find it a priori. You will never find it if you don't know it is there. And in mathematics, this kind of statistic is manifested by some convexity of some parameters, and then there are large spectrum of theorems saying that this concentration phenomenon will have function very many variables, and then with very high probability this function is constant. It's where you can sit somewhere. Of course, sometimes it's not a function, it's still not one number, it may be many of them. For example, if you look at the object in this room, and they're apparently there is definite structure, but if you compare them to the number of molecules involved, they're still essentially constant. The number of parameters describing anything you see here on the global scale is counted maybe in million, and the number of particles in this involved of order 10 to the 30 probably, or maybe 27, right? It's slightly above Avogadro number. So it's still, from this point of view, this essentially constant function. If you see, of course, everywhere in the air, you really say it's more or less the same as constant. When there are objects, it's slightly more limited, but still this principle is there. This was exactly what Schrödinger says about the atoms must be small, but not too small as far as cells are concerned. As I said before, there is some array. So, what is here? This is a. Have you already told this story about this epidemic? So I can repeat it. It's kind of remarkable. It's remarkable problem, and it has, I think, significant relevance in biology, which tells you how randomness can be killed by biology, how a very improbable event may happen by a very simple algorithm. And here is the story which I described, that there are, and there are 100 different infections, and you have to be inoculated against them, and there are places where you can go, but you don't know which place contains which vaccine, and you have to try by some rule, following certain rule, which you can find develop for yourself beforehand, so to find your own vaccine, and so and you're allowed only 50 tries. And so a huge number of people, each of them, which agreed beforehand how they behave, out of 100 they may try 50 location, and what probability that they can find, everybody will find their own vaccine, so if they all come together to a city and there will be no infection, right? And this is seems kind of probability seems to be virtually 0, because it's 1/2 to the power of 50, and 1/2 to the power of number of people. So if there is more than 100 people, it's a huge number. So probability finding for them, everybody would find what they look for looks negligible. However, if they agree correctly, and moreover they agree in a very simple way, then probability will be 1/3, slightly less than 1/3, 0, something like log 2 or something like that. Yeah, 1 divided by log 2, and this is a kind of simple mathematics. And so this is a problem on the internet. You can find it under the name of 100 prisoners problem. Usually it's explained with people being in a prison, but this way is kind of more appropriate and faster to explain because it corresponds to real situation, right? And the point is that what essentially you don't have to. The only agreement should be they must enumerate in some way, then give names to the viruses and name to the place to look for. So they make a permutation in the set of 100 elements. There are 100 viruses, 100 places, and you have to match them, and which essentially it's a kind of permutation, and you have to randomly match them. If there is a random matching between them, and then the simplest behavior, if everybody behaves the same way, the most primitive way, that will work. And either none of them, or most of them will not find what they want to, or with probability almost 1/3, everybody will find what they look for. And this is typical for the biological system. Especially like bodies of big multicellular organisms, there are not so many types of cell. Most cells being repeated many times, and they have the same program. And the program must be very simple problem. And they work in random environment, however, they have to do something coherently and properly. And that is not as impossible as it may look. And arriving at this evolutionary is not that impossible, because you need only a few quadrillion tries, and then you work. And quadrillion is a small number compared to the time when the first organism appeared there in their number. Right, because there are quadrillions, even more than that, quintillions probably of bacteria, and the lifespan was about, they developed in billions of years, so the number of generations was enormous, and 1 trillion, but quadrillion is a small number. And once you arrive at that, and then you beat much bigger number, like 10 to the 100, 10 to the power 100, which is much bigger, with very simple program. And the mathematical issue here to find what are simple programs. And this instance, they're simple, easy to find, and they're kind of very different kind of complexity involved. It's very, on many levels, it is correction of Kolmogorov complexity. Besides, it must operate in a random environment, and secondly, the complexity of probability of finding it by random choice must be also very high. And this is one direction, I think, in mathematics very interesting. And there is some work, maybe I mentioned, that is called PAC, probably approximately correct. And when somebody, I keep forgetting his name, something like vigilant, something like that. I forgot his name. Is a computer scientist who developed this kind of theory for this kind of purpose, but I don't think it satisfies this criteria. Certainly, exactly what his purpose was to make more. Many people actually having this idea, take more quantitative theory evolution to see which is probable. Thinking as evolution is a kind of learning process, and using experience with the learning theory do something, but it's, in my view, is purely abstract. It's purely abstract, completely useless. We need something more primitive and attached to data we have about biology. And this little problem looks to me kind of mathematically promising. So as mathematician, you have this beautiful theorem. What would be your generalization? What are the very simple program which produce unexpected, probabilistically very unexpected results. So I even don't know how to formulate it correctly. There is this example, and you definitely, if you think about this, very excitable, completely counterintuitive, and you want to articulate what in there without being specific, and then you can try to generalize it, to formulate a specific mathematical question here. This is one thing would be nice to have. And yeah, also there are other kind of, I said about cell, here is kind of, if you look at behavior of ants, it's another good example. And each, say, working ants, there's a few groups of ants, usually they all do the same. And something very simple. However, they create very coherent behavior. Or look at termites, which make this kind of interesting buildings. And they all do the same, however, create highly resulting behavior very far from random, though they operate in a random environment. Right? So, and there are this kind of abstract theory called swarm mentality, describing how birds become organized into groups, but this is again algorithms. They're not that interesting as that, because you see the point what this algorithm I describe, which I described, I referred to in this problem about patience, very simple algorithm, but you repeat it many times. So you have to repeat it roughly from 1 to 50 times. You try 50 things, you repeat the same procedure many times, and because many times you arrive at something non-trivial, which you cannot see intuitively immediately. It's not one-step algorithm. It's multi-steps. And this program is simple, implementation is simple, but many repetitions. That's the feature of that. And this is how languages are organized. They have recursion in languages, which is the same kind of principle. Something very simple, but repeated many times. And one, of course, is well seen in how plants grow. They branch, and the logic of branching may be the same on different stages, and more or less the same for all plants. And there is kind of mathematical combinatorial description of that called Lindemeyer systems, and very kind of ingenious programs how we can make trees, kind of symbolic trees, kind of logically how we describe trees. And so this is another instance. But these trees are simple, because there is no cycle there. And similar something with cycle is less obvious. Now, what else? Structure. Yeah, now I want to give a little list of 14 features of biological system, but now we have time. Let me emphasize one of them, which is related to something what I said. So there are two kinds of information. One is information written in, or at least two, written on DNA, which defined, direct your development, and another just we exchange, organisms exchange signals. Starting from the cell, there are intercellular, within cell, anti-cell, anti-animals, and because between people. So there are the signals. And especially on the level of signals, what you don't know that there is information. So what you observe physically, you only see physical results of actions. You don't know what information is. Information is hidden. It's not visible, right? Even if you don't know the language and you see a piece of paper, something written, you can record some points on the paper, but you don't know what's in there. But how you can decide it was information, but not just a random thing there, right? This is only seen in the interaction between different entities. So say you have behavior of animals and what is information, what is not. And what is characteristic from physical point of view, that physically, negligibly, energetically, very weak factors may completely change behavior of a system, right? So cell receives some signals, one little molecule stuck to its surface, and then there is something happening, and cell behaves in a completely different way, huge compared to one molecule. Cell is a huge machine, and the same, of course, applies to animal. There is some smell going to the literally 10, 20 molecules goes to the to the nose of a dog or another sensitive animal, and behavior completely changes. Or it happens also to you. You run in the car in the road, and there is an arrow going to the right or arrow going to the left. And physically, this two things completely indistinguishable, two dots. And then you turn this or that way. The whole machine, hundreds of kilograms, moves because in your eye, some photon from there came here, slightly different shape of photon going to your eye. It's physically absolutely, no physics can live in this way. Yeah? If absolutely undescribable difference. Physically, you cannot say from the point of view of your retina what happens to your cell in the eye because there was arrow in this direction or in this direction, and the whole machine turn. It's indescribable. But this indicates there is information, right? So we have good physical criterion for information, and then mathematically you can say, but what physical system with this property? There's a physical system kind of organized, but very stable and doing some under huge noise. Or you drive lots of things, you see it had no effect on you. But this particular thing changes your behavior. And so what are physical systems mathematically on this way? Have some kind of system, just differential equation. There are some parameters, highly stable for most perturbation, but there are very special perturbations, some particular coordinates, and there are huge number of coordinates there, yeah? Probably a combinatorial number, and changing in one of them, and it completely the whole system change. What are simple design mathematical with this property? And this is kind of interesting problem, right? Completely, we may try to formulate abstractly. And I think there is a class of, and usually people study dynamic people in differential equations, they focus very much on majority of very narrow class of problems. You have something like some transformation of the plane and what will happen there, and just, super special. And by the way, you know that majority of work on papers on differential equation written not by mathematicians, by chemists. And chemists have much better, much broader perspective on that, because they have different reactions, very many parameters. They're concerned with high parametric spaces and how things, exactly what they said, how it works. And there are networks with them, and there are also books written by chemists, and a completely different theory. If you see what they say about differential equation and what mathematicians, especially now, everybody, already many people focus on various versions of stability, which is stability not the one which is relevant for biology biology, and this is different world. But this is, in particular, this is what observed in biology all the time. Where information enters, physically it's manifested by this fact. Tiny little change somewhere has huge effects. Like in DNA, you change one basis, and you're alive or you're dead. Yeah, just only one letter in your DNA. Remove it, and you're dead if it's from some crucial protein. So, on the other hand, still life exists, and still there is stability for majority of perturbations. Can we describe this mathematically? Of course, you can imagine that kind of very simple thing. You may have very simple model. Of course, it works because a biological system has hidden free energy, and this may be released like you have kind of big weight or on a thread, and then cut it, negligible amount of energy, it goes down. And this is what happens, yeah. But you just have to have general principle behind this, and interesting mathematics, it's another issue. If you can make interesting mathematics out of that. Again, it will be not relevant probably to biology, but it will be interesting. Yeah, this was the sky. And so what else there? So. Another kind of interesting mathematics, which is half kind of physical, partly not, it's a design of self-assembly. So chemically there are two basic processes in the cells. One is changing covalent bonds, basically synthesis of molecules using enzymes, and so and what related to enzyme, and certainly you want to understand it, even though this well understanding of the principles probably will not help you to in practice, because computationally still you'll be far from the target. And another is weak interactions, and how weak interaction allow you create new shapes. And this is the basic mechanism. You want to create a shape, so you create some molecule with certain sequences and then self-assemble and create interesting shape. So you have sequences, or molecules, usually protein, they may fold and then they join together. Again, what are possibilities of this mathematically? So you have to try to axiomatize of this, how molecules interact. And then, again, computationally it may be quite difficult, but the principle, I think, not that impossible to describe. And then to try to predict or see how cell assembly happens. And it happens amazingly often. Besides proteins, we have a self-assembly of viruses, self-assembly of ribosomes. Actually, anything is self-assembly, and sometimes, of course, there are intermediate steps. And this is what is done. What are possibilities of this kind of engineering? Imaginary engineering. Yeah, so if you can make it. So it's time to finish. Yeah, I'm running out of my time. Okay, so I don't want to. I put it on. I will edit this and put on my. This part is not on my page, and so. And so from the following two lectures, 1 hour, which will be about Anthropocene and the ecology in the presence of human and what we know and what we expect, and another will be about biotechnologies, where the most kind of positive, the most impact mathematician may have in designing, using means which now develop more and more, biological means of producing interesting structure, for example, interesting cell or interesting molecules, but how to combine techniques which are known. The point is now that you don't use one operation, you start combining them in a particular way, and so you have to invent complicated combinatorial shape. Of course, you cannot do it like that if you have to spend your huge amount of time on that and cooperating with people who know what to do. But and there were kind of remarkable discovery in genetic engineering is CRISPR, which has many problems, which is by no means solved. And some problems are kind of biophysical, which we don't understand how it works, and mathematics there is not developed. And secondly is new techniques of artificial evolution. This is, I think, very ingenious scheme, how we can to make much faster than before, a much more easily program evolution of bacteria and viruses for particular purpose. And again, the question is it's kind of this, what is done can you be used as blocks for more complicated systems. And again, so eventually I think we shall arrive at the way we have kind of biological computers. And this is as chips which were being designed, not perfect for that, and out of them you can make kind of biological system working on computers. Namely, not computing anything, but being programmed, being able to program them for particular biochemical processes, and then design them would be partly mathematical task. But of course, I don't think mathematicians will be involved directly, but mathematically minded people, of course, will be there. So for the last lecture will be about that. And now if you want to ask me something, maybe I will be able to answer, which is certainly not guaranteed. Yeah, because I must say I'm just keep learning, and there are huge amount of things which on the basis I realize I don't understand and have to learn. And both facts and principles, yeah. Enzyme I found mathematically absolutely fascinating, understanding enzyme, yeah, on the quantum mechanical level. It's not understood, and much work is kind of by physicists and mathematical work. So, and those who like this thing like Schrödinger equation and things related to that, it is kind of, I think, field, and it's amazingly, I haven't seen any mathematician working on that. I haven't found anything written by mathematicians. There are mathematical kind of work by physicists, but not by mathematicians. I thought entomology on this level must have more mathematical participation. Yeah, because if you think about how it works, the whole model, I was saying something about that you have this you have to go over potential barrier, and you cannot go over potential barrier, right? If you see in this this wall around you, no matter what you do, you need energy to go over this wall. And the only source of energy is Brownian motion. You have to use it in an intelligent way. And actually, some people argue with that. I don't understand how you can argue with that. There is no other source of energy. Catalyzer that doesn't carry any energy. Right? And
but I thought the enzymes were diminishing the...
No. This empty words, how you can do it? How you can do it? No, and it has no energy. If you have to build to lower, it means you have to kill this energy. You need energy to lower this. No, you cannot do it. You need energy to do that. You and I as well. You have no energy. You're very intelligent.
Chemical binding can change the landscape.
No, exactly. My understanding what they can do. These people say this word, but I think it's completely repeat this word. So you have this, it sits inside of this wall. You sit there, right? And you don't know what this wall is. It's high, right? If you don't have energy, no way you can do it. Right? You cannot change it. However, what you can do, because the wall may be not exactly like that. The energy is like that, but it may be like that. And you see, it's the same energy. But now, in order to change it somewhere, you cannot make it lower. To push it lower, you need this amount of energy. But what you can do the following. And I think what's happening at this kind of more or less. Because there you need very small energy, slightly push it. But now when it happens, now going from here to here is much smaller energy, it's comparable to molecular energy, you go there. But having this hole, you stay there slightly longer. Because this process, going over there if you go, it's femtoseconds or picoseconds. And molecule hits you every microsecond. But if you make it longer, you stay there slightly longer, maybe a microsecond. If you stay microseconds here, second molecule can hit you, and then you go there. So you can use energy of many hits by Brownian molecules. There are some other versions of that. But it's only you can change the time scale. You can play on the fact that this process very fast. You need energy but faster. So, and also there are oscillations of proteins. You can use oscillation, they're also faster. But you cannot kind of cheat it. You just need many kind of molecule hitting you. And the question how to, maybe not molecules, maybe oscillation somewhere else, right? But I don't think it's physically possible to go over the barrier and without energy. It's impossible. I think it's just physically impossible.
The enzyme itself binds and changes.
By energy, it binds, yet energy. It changes position, it doesn't carry energy. Energy connection.
Binding energy is negative.
No, you have to subtract, you have to jump over this. You are here, and enzyme, you're sitting here with enzyme. So what enzyme does? Mathematically, it adds you new coordinate. So with enzyme, you just add new coordinates, you know. This is cheating. I think this is exactly what these words I said, they have no meaning. Mathematically, if you look at that, they're completely meaningless. No, I think people know what I say. Those who know don't say it explicitly. I guess you see these pictures, yeah? They write exactly this picture. And they're called intermediates. But some say, oh, well, there is theory of intermediates. The theory of intermediates explain you how you can change landscape in order to use many hits. But to go over there, you need definite amount of energy. And you can use it using many Brownian hits, right? And this, you need to gain a lot. Because if you have one strong hit, you square your small time. But if you have two hits, you only divide it by 2. And this is what enzyme does. In my opinion, yeah. And it can be organized with this picture, with another picture, but I don't think anything else is possible. You cannot jump out of here. Now imagine, you have anything in your wall, all machinery, but you have no energy. You have to jump over the wall. Huh? And there is a kind of big thing moving around. How you can do it?
In the Born-Oppenheimer approximation, if you put a molecule in the middle, you changes completely the landscape.
No, they have to have such energy. Electric field. Of course, molecules have tiny electric field around this, but the energy is much smaller than this energy. In the protein molecule, there is no hidden energy. There is no hidden energy in any form. You see? If it were, it would break up. It would not work as a catalyzer. Write mathematical model, you see it will not work. Try to write model and you see it doesn't work.
But for example, in quantum mechanics, the particle can...
To tunnel. They can tunnel. Of course, tunneling is possible. Tunneling. The question is the time of the tunneling and how you can change this tunneling. They speak about that. Tunneling is possible. Of course, tunneling, because you may have, again, because this happens on a different time scale. The point is that vibration of proteins happen in the picohertz. Therefore, probability of higher fluctuation is much higher. But still, I think it's lower than this one. Because even if you oscillate much faster, it just gives you this coefficient by 1,000. But on the other hand, in order to have high energy to over error, you still take a power. And so it will be not sufficient to overcome this barrier. In some cases, it may help you, but cannot change the principle. You see, in order to have fast molecule, moving so fast, it's on the tail of the Gaussian distribution. They go super exponentially fast to zero. So one molecule, one hit will not, very unlikely, whether it is tunneling or non-tunneling. It's all on the tail of Gaussian distribution. But what I'm saying is not on the tail. It just multiply only by a constant in this picture, in principle. Again, I haven't made computation, but this looks to me plausible. Anything else just doesn't look to me plausible. Right? Tunneling is a rare event, especially if you have to. Tunneling of electron is, well, okay, but tunneling of a proton or something is highly unlikely. And this exactly corresponds to the idea of intermediates. These are intermediates. They're there, and you spend some time there. And if you spend here something on the level of microseconds, okay, yeah, you'll be in heat. And so, of course, you lose a constant, but you don't take square. There's very small epsilon, and epsilon squared is just with high power, absolutely improbable, but here a realistic constant. And again, I hear these words being said in some articles. They say it without explaining this, my interpretation, that some people certainly know that. Actually, I read the literature, I even know who these people. I was wondering to invite somebody. There is somebody actually called Schramm, who is writing this article, and physicist, who probably one of the kind of, who thought about this a lot. But these people, they know so much, on the other hand, they just presume you understand what they mean. But I think this is what they mean, but they don't say it. Not that it's, I don't think that people who work on that don't know this perfectly. And this is how I understand what they say. But when you look at the textbook, they keep exactly this, oh, you changed that, this empty words. There is nothing behind them. Of course, what behind them is this, yeah. You can change it in this form. You see, you can take small perturbation, right? We can change gradient, right? Gradient change, significant change with the gradient, but it's only variation. But you make small variation in this absolute value norm, but not small in absolute value, but large in the gradient. In changing this landscape, creating artificial local minima, where you will stay longer. And again, just browsing through that, I see this what I said in pieces. I saw it being stated, but never all together. I couldn't find this kind of explained in verse. But I'm pretty certain that some people know that. Actually, even in this area, I think they're probably experts. But I haven't looked in this area. I'll try to find somebody. Or you can invite. From the literature, I know who does it. Yeah. 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 Okay. We'll talk. People. Okay, yeah, I'm sorry.